there is a connection between integration, in our case Riemann integration, and differentiation. And we'll make the connection here explicit. It's done through two theorems, which in a sense are the main theorems of calculus. There's the first fundamental theorem that f be a Riemann integrable function from the interval ab onto R, and uppercase f from the same interval ab onto R be continuous on AB and differentiable. Let's assume furthermore the derivative of uppercase f is actually small function lowercase f for every x in the interval AB. Then the integral of the small function f from a to b, simply the difference of the evaluation of the function uppercase f at b minus the value of the function uppercase f at a. You know this result. This is how you compute definite integrals in calculus. You find an antiderivative of the function, and then you evaluate it both endpoints of the interval, subtract one from the other. So it is fundamental how you do calculus. What do we need to show? Well, we already know that the little function f is Riemann integrable, so we don't need to show that it is Riemann. But what we do need to show is that the difference between this quantity here on the right and the quantity on the left can be made as small as one wants. And so the only way that this can be true is if they are equal. Let epsilon be some positive number. Because f is Riemann integrable on the interval, you can find a partition which depends on epsilon such that the upper sum of this partition minus the lower sum of this partition is smaller than epsilon. Right? That's the Riemann criterion for integrability of a function. Now we apply the mean value theorem to the function capital F. We know it applies because the function is continuous and differentiable on the interval AB. But instead of applying it over the full interval, we are going to apply it to the interval formed by two successive points in the partition. Right? This partition P epsilon here actually ends up looking like x0, x1, all the way up to xn, where x0 is A, xn is B. So we'll look at a subinterval of this partition, which is given by xi minus 1 and xi, and we'll do so for every little subinterval. Push it over these subintervals. Now, what that means is that at some point in the interval xi minus 1 xi, you're going to be able to find some point ti. Assume that this is the right point here. Sorry, I didn't draw this nicely, but it's a point where the tangent is going to be parallel to the secant line between the extremities of the points on the curve of the function xi minus 1 and xi. There exists some point ti in the interior such that f at xi minus f at xi minus 1 divided by xi minus xi minus 1 is equal to f at ti. And typically speaking, here you would have capital F prime, but by assumption, capital F prime is little f. You get this for every I from 1 to n. Let mi, with a little tilde here, be the infimum of the values f at x, assuming that x is in the interval xi minus 1 xi. Capital M tilde I will be the suprema. True for every I. Well, we know that these exist because the function is Riemann integrable. Then the lower sum of the function corresponding to the partition the epsilon would be the sum of all of the infimums over each interval times the actual length of the interval. I've shown you what these values here are for a specific subinterval of the function. And this is, by definition, smaller than or equal to f at ti. Remember, ti is one of these points here. It's the point whose existence is provided by the mean value theorem, times xi minus 1. Part doesn't change. And so here, by the mean value theorem, this is exactly equal to, right? So this equality here is guaranteed by the mean value theorem. Take the xi minus 1 and multiply it here on this side, you get f at xi minus f at xi minus 1. And you know that this inequality here is valid because ti is in the interval xi minus 1, and so in particular f at ti is going to have to be larger than the infimum of the function on that subinterval. But this is a telescoping sum. You write it down, you will get fx1 minus fx0 plus fx2 minus fx1 plus all the way up to fxn minus f at x and minus 1, and all of these terms here will cancel out. The only term that doesn't cancel out, well, there's two of them. There's f at xn here at the end minus f at x0. There's fb minus f. And you can do something of a similar nature with the upper sum. The upper sum of the function for this partition would be the sum of the largest values, capital M I tilde, times xi minus xi minus 1. And now this is the supremum, so this is going to be larger than the sum of the f at ti's times xi minus x minus 1. Same ti as before, the one guaranteed by the mean value theorem, which is equal to, by the mean value theorem, this sum, and the rest of the argument above. What we get here, on the one hand, the lower sum is bounded above by fb minus fa, and this is a lower bound for the upper sum. But you know what else we know? F is Riemann integrable, and so by the Riemann criterion, the difference between the upper sum and the lower sum is less than epsilon for every epsilon greater than 0. That's something we'd already mentioned. And at the same time, because the function is Riemann integrable, the upper sum here has to be greater than or equal the Riemann integral, the function f on AB, which has to be greater than or equal to the lower sum associated with the partition the epsilon. You combine these two things together with what you found here, you don't have a choice. The difference between the integral and fb minus fa has to be smaller than epsilon. How do we know that this is the case? Think about it, right? So here I am on the real axis. Perhaps this point here is the value numerically of the integral. This could be the numerical value of the upper sum, and perhaps this is the numerical value of the lower sum. Now we know that the distance between the upper sum and the lower sum is less than epsilon, so this is less than epsilon. What we found in the previous slide is that fb minus fa as a numerical value is also between the lower bound and the upper bound, so perhaps it's somewhere here. So we don't have a choice. fb minus fa minus the integral of f between a and b has to also be smaller than epsilon. But because we don't know which one would be larger, we'll put the absolute value. Remember though, epsilon is arbitrary. And no matter which epsilon we pick, we can show that the difference between the integral and fb minus fa has to be smaller than epsilon. There's only one possibility here. This quantity equal to 0, which means that the integral indeed equal to big F at B minus big F at A. And you can see how we build the proof using a succession of other results from this chapter. In particular, the mean value theorem is a fundamental building block of the proof of the first fundamental theorem of calculus, as well as the definition of what it means for a function to be differentiable, continuous, Riemann integrable, and the Riemann criterion.